All right, welcome to Full Momentum and HEC-RAS podcast. I am your host, Ben Carey, and joining me today, Chris Goodell, as always, and a very special guest, Robert Schomp. Welcome to episode 29, Robert, of the HEC-RAS podcast.
Thank you.
Great to have you. We're really excited to talk some RAS today. But before we get into some technical discussions, I do want to just let everybody know that's out there listening that this week has been very hard for me and my family because I secured last place in the company bracket challenge for March Madness, and as somebody who watches way too much college basketball and pretends to know a little bit about college basketball,
Ben.
it was a tough week, Chris, and I know you
Ben,
had some success. So
Ben is he's the manager of our office bracket pool, and so he gets this thing rolling every year. And hey, despite your last place finish, we all still think you know the most about college basketball in our group, in the company. But yeah, I had a period in the middle there where I was like, I think I could win this. I was bumping around first or second place, and as always happens, you get your hopes up, and then you have one of your big teams loses later in the conference tournament, and that's it. And I think I ended up 15th or something like that.
We have the biggest problem is our company has way too many people in the Northeast, so we had a lot of UConn fans in the bracket challenge, which makes it an uphill battle.
I should have known that when I was picking mine, but
yeah.
Anyway,
so I want to come clean to everybody because again, we do talk a decent amount about college basketball on this podcast, and please do never listen to me about my picks because apparently that will lead you down the wrong road.
I think that's a real thing, though. You can overanalyze when you do these, and you may be very correct in picking the team that should win, but that doesn't always happen in March Madness, as we all know.
Well, speaking of overanalyzing, we're going to have an interesting discussion today on 1D and 2D river restoration modeling. So that's a good little segue into a preview of what's to come later on in this episode. But before we get into that, I know everybody's probably thinking, hey, I know who Chris is. I know who Ben is. Who's this Robert guy? So Robert, again, we're really happy to have you on the podcast. If you want to start off by giving folks a little bit of background info on yourself and how you ended up on the podcast here today.
Perfect. I really appreciate the opportunity. I was nervous this morning to join the ranks of people like Grady Hillhouse and Stan Gibson. So I'm really excited to share what I've learned from doing my work here at Kleinschmidt, especially as it relates to 1D HEC-RAS modeling and stream restoration. I'm Robert Schomp. I'm a hydrology and hydraulics engineer with Kleinschmidt, and I've been with Kleinschmidt for nearly 3 years now. Most of what I focus on is flood risk assessment. I've been supporting some water rights adjudication projects, which include surveying and digitizing that data into 1D HEC-RAS models. I've also been getting into sediment transport and learning all the ins and outs of doing sediment transport, both in 1D and 2D. So that's been a very unique challenge, and it's been very fulfilling work to kind of push the boundaries of what we know about sediment transport and what we can do with the results.
Yeah. We purposefully had Stan on before you, Robert, so that we didn't put too much pressure on Stan to follow up a sediment transport legend like yourself on the
podcast. I appreciate it. Make the playing field a little more even.
So that's a little bit about what you do here at Kleinschmidt. Just out of curiosity, how did you get into the field of engineering and water resources overall? I know you got a lot of different interests out there. So how did you kind of settle on that, area of expertise?
Yeah, that's a very good question. Over my years in college, I attended 4 different colleges. The last being the University of Texas at Austin, where I got a master's in civil engineering with a focus on water resources and environmental engineering. But my passion for water and water resources engineering actually started at Oregon Tech as I was a new student in the renewable energy and engineering program, where I learned a lot about hydropower, how dams impact streams and rivers all across the US. And I was just absolutely fascinated with that type of infrastructure because it's complex. There's no optimal solution between all of the interested parties for those projects. So I find this type of work very fulfilling because we get to be creative and get to propose unique solutions that try to, accompany all of the types of interests that people have for these projects.
Very cool. Well, I know speaking for myself and probably Chris as well, we really enjoyed working with you ever since you've been at Kleinschmidt, and we're really excited for you to be able to showcase your experience and knowledge to the HEC-RAS world here on the podcast. So thanks for taking the time today.
Yeah,
Yeah, Robert sits right next to me in the office, and so we naturally have a lot of conversations, work related and otherwise. And Robert has probably the cutest dog I've ever seen come into the office.
Whoa. Come on, Chris.
Besides Rui, of course. I mean, that goes without saying. But it's just, first of mine. So that's all. I mean, Rui was the cutest when she was coming in every day. But Marge, Robert's dog, is probably the only living being in our office that has more energy than Robert.
Ooh, good point.
I think. Yeah.
Good stuff. So. Awesome. Well, let's go ahead and get into some questions that we got from the audience over the last couple of weeks on LinkedIn and YouTube. Before we get into those, I do want to give a quick shout out to our sponsor. We're thankful to be sponsored by our firm, Kleinschmidt Associates, who's known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. Thank you again to Kleinschmidt for supporting Chris and I and for supporting Robert to be on the podcast today. Awesome. First question, Chris, that we got from the audience that we wanted to touch on was kind of a follow-up to the 2D bridge conversation that we had last month. I think we covered a lot of ground there, but there was somebody who wanted to know a little bit more about how to view specific output through a 2D bridge when you have a 2D bridge set up as opposed to a bridge set up in 1D. As we all know, there's the ability to get pretty quick instantaneous output data for 1D bridges within RAS, and it's a little bit trickier to do with 2D. So why don't you share with folks your recommendation in terms of how to do that?
Yeah. So, I mean, bridges have been around in RAS for a very long time. Since before I used RAS, they've had bridges, and they go way back even into the HEC-2 days. However, that's always been 1D. And when 2D came out, they did not have bridges as an option for 2D areas. And so we had to get a little bit creative. Now we do have bridges in 2D. So it's really nice to have that feature, but it's still improving. There could be better ways to look at output. And I think that's probably the crux of this question is, hey, how do I look at my 2D bridge output? Because I knew how to do it in 1D, and I can look at it in RAS Mapper for 2D, but I don't know how to look at the bridge and section view and see the water go up and down and things like that. So let me first show and talk about how you do it in 1D, just so we can kind of compare and contrast here. So this is a real simple model, Beaver Creek bridge model. You get this with the example data sets. It's a pretty schematic looking reach, and you've got a single bridge down the middle. And we can look at the input for that bridge in the bridge culvert editor. There's our bridge. If I zoom in on it here, you can see all the different piers that have been added in. You can look at the bridge modeling approach as well and see what equations we're using for this particular bridge. All right, so that's 1D. And when you run it and you want to look at results, well, you can always go to the cross-section viewer, which is right here, this button. And there you can see our bridge. And we can animate the results. Of course, I haven't run this yet, so let me give it a quick run. This should go pretty quick. But once it's run, then you're able to see the water surface elevation on the cross-section viewer plot itself, which is really helpful when you want to know, hey, is my water getting high enough to touch the bridge? Or is it going over the top of the bridge? Am I using the right equation as a result? So that's always a really convenient and effective way to interpret what's going on in your model. The other thing you can do too is you can look at velocity distribution within a bridge, and you can see, hey, do I have velocities concentrated around the piers and that kind of thing. That can be important for doing scour analysis. So if I open up the cross-section viewer, now I can see my water level there. I can, in an unsteady flow model, you can animate it and you can watch the water go up and down in your bridge section. There we can see it's overtopping. So it's not only going pressure flow, but it's overtopping as well. And it comes back down. Okay, so people were used to this, comfortable looking at bridges this way. You can also look at the stage and flow hydrographs as well for a bridge. So if we click on that button right there, that pulls up stage and flow hydrograph, and I can go to my type bridges culverts. And here I can see how the stage on both the headwater and tailwater side of the bridge changed throughout the simulation. I can also see what the flow rate is through that bridge for the entire simulation. You can pick out some important values like maximums right here in the table, or just go right to the plot. All right, so everybody who's been doing bridge modeling forever is really comfortable with this. They understand how to look at bridges in 1D, but now that we have bridges in 2D, how do we look at bridge results? So let me open up a 2D version. That this is the Bald Eagle Creek data set. So different bridge here. And this bridge happens to be in a 2D area. So notice I'm using 6.5. Where did my RAS mapper go? There it is. Okay, so here's our bridge. If I zoom out a little bit, you can see more of what's going on here. There's another bridge right there. So there's several 2D bridges in this particular model run. There's one there and another one there. This too is an example data set that you can get a hold of when you download the software. So it's great. You can see the bridge. I can turn on my velocity map, my velocity output. I always like to look at that when I'm troubleshooting and evaluating my model results, and I can animate. And this gives you a great view from a plan view perspective, what's happening around the bridge. But it doesn't tell you everything, and you can't see the section view here. So a lot of people ask that question: how do I see the same plot that I had for 1D in the cross-section view, or how do I see that here? Well, if you go down to and turn on your results here, and make sure you turn on your geometry under your results plan. Okay, not the geometry up here, but turn it on under the results plan and turn on your SA2D connection. Okay. When you have that turned on, now I can right click on it. I'm gonna check water surface as well. I can right click on it, and at the very bottom you see it says plot SA2D con data, all enabled results. So these are my enabled results, velocity and water surface. I can plot it. Of course, they haven't set it up yet to look at velocity as far as I can tell. So you're only going to get water surface for now, but at least you have that. So when I click on that, it pulls open 3 plots. It gives me a center line plot right through the middle of the bridge. It gives me the upstream face of the bridge and the downstream face of the bridge. And I pull up my RAS mapper again. Where did it go? Oh, there it is. It's hiding there. All right, so we have the 3 windows open here. It's showing upstream, downstream, and center line, and I can animate these if I have the right things selected in here. So if I go and look at RAS mapper, I wish it would let me put these up front. So let me minimize these real quick. So you want to select what you would like to see. Now they're not going to be able to show you velocity yet. I think that's coming in a future episode, or if it's available now, I haven't figured out how to use it, but you can definitely look at water surface elevation. So I'll just turn off velocity. But if you want to animate this in those section views, you have to make sure that you select the plan name up here as the active layer, not the water surface, not the bridge here, not the SA2D connection, but the plan name. That will allow you to see these 3 different plots going at the same time. And so if I bring those back up, okay, here are my 3 plots. This is my downstream. I'll put this over here because that feels like more of a downstream side. And that's upstream, and there's a center line. Now I can animate, and we'll see these water levels go up and down. Okay, with the simulation. So in this particular example, it doesn't hit the bridge deck, but maybe if we ran it longer, it would. But you can clearly see how it's interacting with the piers. And the nice thing about 2D, obviously, over 1D is you can have variation in the water surface going across here, which you can clearly see. You wouldn't get that with 1D, especially when you have piers and those kinds of things in there. They can have a big impact on the lateral water surface elevation and velocity distribution as well. So that's a quick way to take a look at your bridge output, 2D bridge output in section views. What do you guys think?
Yeah, I think that's really helpful. I think it's a good tool, especially the animation part of it, because it's a little bit tricky to find right now. I know, Chris, though, one of the other things that I was thinking about when I heard this question was the actual numerical output for the bridge. So, for instance, if you go back to the 1D bridge RAS project that you had open, um, obviously you're familiar with the bridge detailed output, which is that table next to the full detailed output. So not that one, but the one next to it.
You want the detailed, yeah.
Yeah. So that is obviously great numerical data that you can get for any one-dimensional bridge. Gives you a lot of different numbers to potentially use for design or analysis and whatnot. Is there a way that you can get similar numerical results for a 2D bridge?
Yeah, there is. It's not as plentiful as you have in 1D. Let's see what happens if I right click on here. You can see plot structure variables. That allows you to get into a hydrograph plot. There it is on my other window. And so similar to what I showed you in 1D, you can bring up a stage and flow hydrograph plot that way, and that allows you to also look at that data by table, but that's really just going to show you headwater and tailwater stages as well as flow. Now, what you were talking about is all the other stuff in the detailed output table that we can look at for 1D, all of this stuff like, the queue, discharge out into the different parts, bridge versus weir, bridge opening area, velocity total, all these other things in here. That's not yet available easily in RAS 2D. A lot of this stuff you can get to if you dig into the HDF file, but that takes a little bit of work to do that. So, yeah, this is one of the things I was talking about, that they're still improving and adding new features and that sort of thing. So hopefully in future versions, we'll be able to do something more like this detailed output table in 2D.
Cool. All right, next question that we had from users was around editing Manning's N values for a 1D model. And this particular user was having some trouble doing that. And so obviously it's hard to troubleshoot for somebody without seeing their model, but I thought we could just go through a really, really brief overview of the different options that are available for modifying Manning's N in 1D.
Yeah. So first of all, if you're in 1D, your N values, they reside in the cross-section editor. So I've clicked on that, and there's a couple different ways that you can define your N values. One is called kind of the traditional 3 subsection method, and the other is horizontal variation. What we're looking at here is horizontal variation. And I know that because when you do horizontal variation, it adds this third column right here. And you can put as many N values in your cross section as you have station elevation points. If you want to, I would never do that. That would be silly and way overkill, but technically you could do it. But by doing horizontal variation, that frees you up to have more N value definition than just the 3 subsections, which you see right here. Okay, now to switch between those, you would go to options, and right now we have horizontal variation. I can uncheck this And it's going to give me a warning that I'm going to lose all this stuff, but I'll just say, yeah, that's fine. And now it's assumed what I want to have for my left over bank, my main channel, and my right over bank. So now instead of having these 4 N values like you see right here, when I apply data, now I just have left over bank, main channel, and right over bank. So this is where you see the N values, and this is how you do different ways of distributing N values. I always like to tell people, if you can get away with just using the 3 subsections, then do that. That keeps things a lot simpler, especially when you start getting into interpolation of cross sections, because your N values also get interpolated. And when you have horizontal variation in N values, you can end up with interpolated sections that have a lot of N values broken up in there that are not necessarily very accurate anyway. And it gets really messy. So I always like to encourage you to try to do the 3 if you can. But, hey, if you've got different roughness out at the edge of the floodplain versus kind of near the bank, then you should account for that. And you can do that by going to horizontal variation in N values.
Yeah, one of the other things I thought would be worth pointing out is oftentimes reviewing and modifying Manning's N values that you have for a model, especially if there's a lot of cross sections in it, can be pretty overwhelming to do that one cross section at a time. So one of the other helpful tables that I reference quite a bit is the Manning's N table, which is accessible under the geometry data editor under tables, Manning's N. If you pull that table over, it'll show you if you have just a simple left over bank, right over bank channel distribution for all of your cross sections, you would just see 3 N values. In this case, you can see most of these have spatially varied N values associated with them. But this is a really quick and easy way to QA/QC. And it also highlights the values that are kind of defined as in channel here. So you can review, make sure that your channel values are consistent, because oftentimes they should be, and then you can have some variation in your floodplain based on land use characteristics and other things. So this is a really, really helpful table for references. One of the other follow-ups to that question, Chris, was in regard to values, Manning's N values of -9999, which is kind of a default, basically null value that you can get for Manning's N cross sections. Is that right?
Yeah, absolutely. Sometimes you'll see that. I see that occasionally. Well, I don't want to say occasionally, but when I'm doing pre-processing of my cross sections in RAS Mapper, but I don't do my N values over there. I don't have an N value layer over there, and so I bring my cross sections into the geometry window. RAS doesn't know what to do with N values, and so it'll drop a -9999 at the first cell, and then all that means to you is that, hey, there's not a real N value here yet. You haven't input it. So let's go ahead and do that. So it's just more or less, I don't know why they picked that number, other than it's probably so not an N value that you would use that it makes it obvious that you need to fix that. And so, so if you ever do see that, that just means, hey, you haven't set your N values yet. So go ahead and do that.
Yeah, and again, I think that's most common when you generate the cross-section features within RAS Mapper, which is something you can do. You can get the shape of the cross-section. You can also get the Manning's N for the cross-section if you have a land cover layer established in RAS Mapper. But like Chris said, if you don't, you're going to end up with kind of those no values for your cross-section. So just be aware of that as you're pre-processing your cross-sections in RAS Mapper. So great question, and thanks, Chris, for giving us some visual answers to both of those. I would fully expect there to be some continued improvement in terms of the 2D output that's available, because I know that's an extremely popular feature within RAS.
I've got a question for you guys.
Okay.
With respect to N values, what is your default go-to N value for a river? I think everybody has a number that they start with, and then they look at, okay, well, what's going on with this river? Is there a lot of vegetation? Is it steep? A lot of boulders, or is it really smooth? What's your starting default? Because I have one, and
I have one.
And if you don't have one, then do you have one?
Like Jeopardy? Should be.
No, I think we'll go around and see how close we are to each other. So Robert, why don't you go first, and then I'll go, and we'll let Chris finish it out.
I usually try 0.04 first.
Okay.
That's my go-to.
Mine is 0.045. my starter. So
mine is 0.035, and I just realized that we're the three biggest nerds right here talking about this, but it is interesting to know where that came from. And like for me, I don't know where that came from other than maybe my very first RAS model, the river was 0.035. I don't know. But yeah,
yeah,
it's kind of
I
interesting, right?
I think the reason the reason that I use that value is because I think 0.04 or 0.035 is probably a little bit more realistic, but I always tend to use a little bit of a higher maintenance end
Mhm.
value so my model's more stable.
Uh,
So
that's funny.
it's a little bit of a learned crutch, I guess you could say. But that's
And
typically where I'll start.
higher end values do give you more stability. That's for
Mhm.
sure.
Yeah. Anyway,
Um,
that's a really good question, Chris. That's fun. So
yeah,
if
and
it
it's funny how we all start there, but then you kind of adjust as you go, and depending on what features you've noticed in your river and stream. But yeah,
yeah, well, I think that's a great one to solicit some feedback. Maybe we can answer
yeah,
have that as a poll question this week. But if you are so inclined, it'd be really great if you could comment on this video in the YouTube channel or on LinkedIn with what your default river value is for Manning's M value. Be interested to if it's similar to what Chris, Robert, and I use, kind of around that 0.04, or if maybe it's something a little bit different. So go ahead and comment on that, and we might elicit a poll question here to get a distribution of values. That'd be kind of a fun exercise.
yeah. I bet people who work up in the mountains probably have a much higher default.
Yeah, for sure.
Yeah.
Cool. Awesome. Well, a couple quick announcements before we get into the primary topic of discussion today. First, on the class front. So, as a reminder, Chris and I have a couple of upcoming classes that you can sign up for today. The first is our in-person class, which is going to be held in Atlanta, Georgia, uh, September 10th through the 12th. I believe that's a Tuesday through Thursday. And
Yep.
it's looking more and more likely that we're going to have our 2024 Pub and Grub attached to that event. So if you're interested in learning about RAS and then attending a night of RAS conversation presentations and a few adult beverages, it's a really, really good time. We've had some really great turnout for those the last couple of years. So mark your calendars if you're in the Southeast, September 10th to the 12th. We will be in Atlanta.
I hope it's not going to be hot at that time.
Oh, it's going to
It's
be hot.
not
Yeah.
dead middle of the summer, but yeah, it's Atlanta can be hot. But I love Atlanta. It's a fun city. It's a big city, and we're going to be right off of the Georgia Tech campus, that area of downtown Atlanta. So I guess it's probably not technically called downtown, but it's pretty close. But yeah, come join us if you want to have some 2D training. This would be a good one to come to. It's going to be a lot of fun.
Great. And then our next online class offering is going to be our standard 6-week course, which is 1 day a week of lectures with workshops in between. That's going to run from October 9th to the November 13th. That is also available for signups. So
Yep.
if the in-person class isn't your speed, or maybe you can't pull off work for get out of work for 3 days, then that's going to be a good option for you too. As always, if you have interest in training in an area near you or for your company, you're welcome to reach out to Chris or I, and we can always set up something, just for you, customized, depending on what your or your company needs are. Also on conferences, reminder, Chris, in just a couple of weeks here, we'll be at USSD in Seattle, Washington. That's going to be April 22nd through the 26th. If you want to swing on by the Kleinschmidt booth, say hi to Chris, ask him some nerdy RAS questions, tell him what you use for your default river Manning's end value. Chris will be there along with some of our other H&H coworkers. So
Yeah,
swing
and
by there.
come do the 5K with me. I was informed by our conference committee lead that I will be doing the 5K. So
Yeah.
I'll be running. Yeah, we'll see how that goes.
Very good. And then I will be at ASFPM National Conference in Salt Lake City in middle of June, giving a presentation there on some HEC-RAS work that we've done here at Kleinschmidt. So I'll be there with a coworker. If you're going to be at ASFPM, it'd be great to see you and connect at that
Where's that
conference.
one again, Ben?
Salt Lake City.
Salt Lake City.
Yeah,
Nice.
yeah. Going to
That'll be a good place.
I already got my times. I'm picked out to go to Red Iguana, which is the best Mexican food. Uh, best Mexican restaurant I've ever been to in the United States. So
Really?
yeah, it's
All
pretty
right.
phenomenal.
That's good
Have
to
you been
know.
to Red Iguana, Robert?
I have, and it's the only place I've been in Salt Lake City.
It's
We hit it
ripping
up on
good.
a road trip, and
Yeah,
it was incredible.
yeah. Robert has a real connection with the Oaxacan region of Mexico. So I don't want to say that it's probably the best mole that he's ever had, but it's definitely the best mole I've ever had. So yeah, cool. And then lastly, trivia question. I told you I was going to get you guys today because Chris has got me a couple times. But this is a softball.
Let's
I
see.
think you guys can get this. So there is only one RAS file. All the files associated with RAS have extensions, right? So the restart file is .rst. The output file is .o, right? HDF file. There are only two files that have the exact same extension in RAS. Do you know what they are?
Oh, I see where you're going with
Yes.
this. Robert knows? Okay, Robert, I'm going to give you the accolades here.
I believe it is the .prj files.
That is correct. Ding, 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 ding. Nice. Well, Robert, you can go ahead and leave now. You're 100% on RAS trivia, so it's only downhill from here.
Yeah.
Chris, did you get that? Were you going to get that one too?
Yeah, that was going to be my guess too. It's really it's always comical that they have the same projection and how often people try to
So
open a
many
projection
times.
file or they try to use a RAS project file to set their projection. But
Yeah.
yeah, so my question is who has claims to being the first one to use that project or that extension, you
What
think?
do you mean? What do you mean? Who has claim? Oh, I would assume it's
Yeah,
the project.
the RAS
It's got to be
project.
the
Yeah.
projection because people
Well,
were
because
defining spatial references long ago.
yeah, but were they doing it electronically? Like, because RAS
That's true.
goes
Yeah, I
the
don't
HEC-RAS
know.
goes back to the early mid '90s, and we weren't doing. I mean, maybe
What were
some
you?
people were doing GISM, but not a lot of
Yeah,
people were.
that's an
So
interesting one. It'd be interesting to ask Gary that.
I think they should fight it out to see who gets to
Yeah.
claim PRJ and make the other one change it.
I know, right?
Well, actually,
Uh,
I see CRS used a lot for projection files too, so maybe they should just
Mhm.
change it to CRS. Makes
yeah,
more sense because it's more than just a projection.
yeah, yeah. Agreed.
Uh,
Good. Well done, Robert. That was probably a little bit too easy. I should have got you on that one, but
No,
well
that's
done.
okay. I'm recently refreshed because as I get into sediment transport, I had to relearn a whole new batch of file extension
Yeah.
names. So
yeah.
I'm always talking to Chris and others at Kleinschmidt about what's in this model. What are these files? So
Very,
Yep. Yep.
very good. Well, let's get into the primary topic for today, which we're, the primary reason we have Robert on for this conversation is because of some of his unique experience that he's gained over the last year or so working on a cool project that involves doing some restoration modeling, but in 1D, which is not something typically that you'll see. It's less and less common now with the robustness of the 2D RAS engine and kind of some of the detail you can get within 2D modeling. You see a lot more people kind of go in that direction for restoration modeling. But just like anything, I think there's still a place for 1D modeling when it comes to restoration. And so we thought it'd be prudent to have Robert on to discuss his work, some of his experiences, and then we can get into some of the conversations around, when 1D modeling is still going to be a good tool to use for this type of project work. Before I turn it over to you, Robert, to share kind of your experience and what you've learned, I did want to share the results of a poll question that we asked related to this topic, and that was, you know, how do you represent restoration features within RAS? We had a number of different options up there, some of them 1D, some of them 2D, some of them energy dissipation related, like Manning's End, some of them physically related, like terrain modifications. And the answer to this surprised me a little bit. 75% of the people that answered that poll said they simulate restoration features using the newer terrain modification tool that's available in RAS. So actually making those physical changes to your terrain to account for the form loss, right? That's you can get within 2D RAS. So that's interesting. We'll maybe talk a little bit about the downsides or upsides to that particular approach. But Robert, if you want to kind of give a little bit of background on and what you've learned with doing restoration modeling with 1D, going back a little bit in time. So.
Certainly, I appreciate it. Yeah, the project I've been working on includes many examples of river restoration conceptual designs. Um, Most of it has been done in 1D for two main reasons. A model that we received previously was built in 1D, and it's very robust and it is extremely detailed. So it was important for us to continue that work, especially because it was calibrated and reviewed, tens, if not hundreds of times. So
Yeah.
it was important to continue using that same 1D model. The other main reason is my mentor, one of my mentors here at Kleinschmidt, primarily works in 1D. He has many decades of experience and is very, very comfortable with 1D modeling. And I think that has benefited me because a lot of what you can look at in 1D, you can back calculate or quickly find the source or reasoning of why the model is doing what it's doing. Not saying that that can't be done in 2D, but I feel like it's readily available in 1D. So it's been a very good learning experience where all of these simplifications we're making to make the 1D model work has been informative to me in how you represent stream restoration elements in a river.
Yeah, one of the big challenges that Chris and I always talk about with 2D modeling is the fact that it's a little bit of a black box, right? And that's a challenge for people, especially as they get into troubleshooting and digesting the results of their model. It's kind of hard to explain how that's computed, right? Versus with 1D, like those are established equations that you can, like you said, Robert, back calculate using hand calculations to check the results of the model, check the work. And I think there's some real benefits to that approach, especially for, a younger engineer who's kind of growing his understanding of fundamental hydraulics, right? Jumping straight into 2D might be a little bit of a disservice. And I know that's happening a lot.
I'll share my screen here. All right. So for everyone who is watching this as well, there will be many ways that this information is visualized. So if this first initial CAD drawing isn't compelling because it looks like a bunch of lines and information, I promise I'll be showing versions in terrain format as well as satellite imagery. So it'll be reproduced in many different ways. What we're looking at here is an example of a conceptual river restoration design with many different elements and features that you might see in other river restoration projects. So we have a river moving here from the left and up to the top. We have multiple different elements. Right here is a boulder field, boulders being maybe like 2-3 foot in diameter to increase roughness. We have a log jam with piles acting as an obstruction to flow on the inside of this bend. And we also have embedded logs with boulder ballasts that are positioned here on what is a gravel bar. And this gravel bar here is defined by kind of these are topographic lines. So this is an area where the river is split into two main channels.
So Robert,
yeah.
I got a question for you. So you've got 3 different restoration element types in here.
Mm-hmm.
You've got the rock outcropping at the upstream end. You've got some log jams, it looks like, on the left bank,
Mm-hmm.
and then some trees laid out in ballast by rocks right in the middle. What are some of the things that you're looking at with the existing stream to make you want to put those there?
Yes, that's a very good question.
Versus somewhere else, or what dictates one type versus another?
Definitely. Yeah, there's a lot of engineering intuition that goes into choosing the elements for stream restoration sites. This one is specifically, and as I identify a pattern as I work on more and more projects, a lot of what you're trying to do is slow the water down. You want gravel to deposit in areas that are currently being scoured. It's obvious here that at this site, we're going around almost maybe a 110-degree bend. So it's important to slow that water down as it goes around the corner. to create habitat and refugia for migrating salmon, juveniles going downstream and adults returning in the fall. So some of this in this split stream is we're trying to create a slower part in the split channel so that we have velocities that are more conducive for salmon traveling up and downstream in this river. We also are trying to reduce some bank erosion. That's not our primary objective. The primary objective is to increase spawning habitat in this river. But as a byproduct, we're probably going to reduce erosion on this outer bank of this bend.
Yeah, and you definitely don't want to put in some restoration features and then come to find out they initiate some sort of erosion event. And right there at the outside of the bend would definitely be something to keep your eye on, right? Because you would expect more erosion over there. So,
yes, that's a very
okay.
good point.
Okay.
And we'll actually see that. That's a good tee up for when I start showing the results. You'll be able to see how some of these features affect the velocity and water surface elevation at this site,
Yeah.
and how they, even though it's 1D and it's all backwater calculations, 1D still can represent some of the interactions between these elements, at least in a simple way.
Mm-hmm.
So let's now go to HEC-RAS. I'm assuming the audience is familiar with what a terrain visualization looks like, where here we have white being higher elevation and these lighter blues being the main channel bed. This is just a representation of how we've gotten the CAD design into the HEC-RAS RAS mapper format, just by using shape files and spatial references, so that we could see now how do these elements that have been drawn, in their own space in CAD, and how do they line up with some of the one-dimensional cross sections that we already had in our model.
One question, Robert, on that.
Yeah.
I just thought of just now. You mentioned the fact that this is an existing 1D model. You wanted to keep kind of as much as you could because of the quality, the calibration, and whatnot.
Mm-hmm.
Did you end up actually adding any additional cross sections for the restoration site itself, or were you able to kind of capture everything you needed to with some of the methods that you're about to describe?
Yes. It was important to retain the cross sections in the exact same format, both for the integrity of the model that we received, but also because, as you can see in this image, this digital elevation model is essentially hydroflattened, or the LiDAR couldn't penetrate the water. So this river, although it has varying depth across the channel, you can't see that in the terrain, or at least the terrain that we were able to receive. So these 1D cross sections actually have surveyed one-dimensional station elevation transects. So we needed to keep that information in the model and try to best represent it through other cross sections. That said, of course, the number of transects was much less than what we needed to represent the density of these river restoration elements. So we did add interpolated cross sections to the model in order to try to capture the features as they might appear hydraulically in the channel.
Makes sense. Thanks.
Mm-hmm.
Yeah. So let's look at one more visualization. This is the satellite view of this site. Not much to see because there's shadows, but one thing I want to call out to attention is that gravel bar I was discussing on the first couple of slides. Now you can see it, how that might exist in satellite imagery. So to give an example of how we implemented these elements in the 1D model and what kind of results we are able to get out of it, I wanted to focus on this specific cluster of elements, being the log with boulder ballasts and the log jam structure with a flood fence, and see how that specifically is modeled along this transect that we've put into the model. So this is this is a sharper view of the CAD drawing, the conceptual design. We can see those these two elements here, and what they end up looking like in the drawing design is you have your log jam here with crisscrossed you have your bowl and your trunk or your root wad combined, and then you have piles interspersed between those logs amongst that structure. And then also with the embedded ballasted logs, we have a log that's embedded with the bowl side down into the gravel. We have a boulder on the tip of that log to weigh it down. And then we also have boulders to weigh it down where it breaches the surface and actually this is the part that adds roughness to the channel. This is the part we're most interested in, its effects on the river as a restoration element.
So the trunk is 2/3 of that is just to anchor it into the ground, right?
Correct.
And then the part
Yes.
sticking out is just for roughness and flow complexity, right?
Correct. Yep, exactly. You hit it.
Okay.
Roughness and flow complexity. And flow in this scenario is going from right to left for both of these. So flow is hitting the root rod side of the trees first.
Now, Robert, I look at this and, right away, especially that drawing on the left, like that's a very complex, detailed design element, right? And so my, HEC-RAS 2D lizard brain is going off saying, how can you possibly model that in 1D? That's so complicated. There's no way you can account for all the complexity of that with a 1D cross section. How did you guys approach, that particular problem, which I'm sure a lot of people kind of come upon when they're deciding whether to do 1D or 2D?
Yes, that's a very good question. I'm sure as you have seen and the audience has seen that this is a hot topic on research, and it has been for a while, but there's been so many papers coming out about these, multi-log jam features and how flow interacts with them, how they add roughness to the river. What you're about to see next, how it's implemented in the model, will be probably the simplest version that you'll see them implemented, but there is such a wide range of ways to model it. Even in 2D, Chris has shown us that you can model it with piles, actually trying to get the features as individual elements. You can model it with Manning's N as a Manning's N refinement, as many people do in the workshop 3 of the HEC-RAS class. And then people also have CFD, computational fluid dynamic models, to really get into the nitty-gritty of this. The question is in terms of cost and time efficiency, what is good enough, right? For example, part of my project this spring was looking at the calculations of drag and buoyancy on these structures. And many of the equations that you can find, both modern and kind of the classical equations, have factors of safety of 3 or 4, because there's a lot of variability in these trees, in the water surface elevation, construction methods. Once you start working in a channel, it becomes increasingly difficult. So to say that what we attempt in 1D isn't good enough is difficult when you have a factor of safety of 3 being applied to your calculation. So a lot of it is a optimization of cost efficiency and accuracy in what you're trying to achieve. That's a good question. There's so many ways to do it. Do you guys have any thoughts on what you might use?
Well, I'm going to save my thoughts until we see some of the 1D representation that you have for these. So.
Yeah, well, the results that we used were informative for our designs, but they weren't calibrated. So I don't have an ultimate, comparison, but we'll talk about what that looks like.
It's interesting, Robert, about the image in the upper left where you're showing the wood, the flood fence. Is that what the orange circles represent? Is that the fence, or is the whole thing considered a fence?
Typically, the flood fence would be just upstream of this element. So a flood fence would, I believe, the main purpose would be to reduce scour that would be occurring at the bottom of the structure.
Okay.
So I believe a flood fence would be implemented in future designs or as an alternative to this type of structure. This is generally the log jam part of it.
being a HEC-RAS modeler, what I really
Mhm.
like about that design is that's easily modeled in RAS because we can put in piers as terrain modifications, right, to represent the vertical anchor logs. And now in the current version of RAS, we can put in little tree modifications or big tree modifications for that matter. And so we could lay those out in that matrix pattern like you see right here and replicate this pretty closely in RAS right now with terrain modifications.
Well, I'll push back on that a little bit and say I don't know if it can easily do it. You might be able to easily add the modifications. The challenge becomes doing that for multiple proposed features, having small enough cells to capture all those elements individually,
Well, yeah,
and having a
that's
model
true.
that still runs efficiently. And I think that, ties in a little bit with what Robert's about to show us in terms of, the 1D representation. So,
Yes,
Yeah.
prepare to be shocked. You've never seen this before. So how we represent those features in this iteration of the conceptual design is using the obstructions feature. Each of those two log jams are two being these two individual, with one kind of being higher up the slope and one being a little bit lower on the slope. We represent with just obstructions built straight into the 1D transect.
That would be the 1D version of terrain modifications, right?
yeah, good point.
Yeah.
Obstructions. Yeah.
You're just taking a slice. And of course, how these obstructions operate is it completely blocks flow. There's no flow moving through it when it does its computation, which is a conservative result. So when you talk about computational fluid dynamics and even 2D, it is just still conservative to say that no water is moving through that feature. In combination with the obstructions, we increase the Manning's end value to 0.1 to indicate an increase in roughness in this area. To represent the embedded log structures, we do not represent that with obstructions because they are a little bit more open to flow moving through them and amongst them than a logjam feature would be.
Especially if there's debris, that gets caught up and stuff, right?
Exactly. Yeah, and a logjam feature is similar to what you would actually see occurring naturally in places. And embedded ballasted log, maybe a little less frequent, but definitely it can occur. But they're more sparse, right? When you have just a huge old growth type tree just embedded in a river.
Was there anything to the value of 0.1 for the Mannings that you guys chose there? Is that just based on experience or any sort of calculation?
It was partially based on experience. My mentor that's been helping me with this project chose the value of 0.1. I think it's reasonable, but I'm sure that there's an academic basis to using 0.1. But we just had the discussion on what Manning's end do you use to start with the river. 0.1 might be his value that he uses for debris.
Well, it's interesting because 0.1, kind of in that range, 0.08 to 0.12 is kind of the numbers you're using for a forest, right? A riparian forest.
Yeah.
And what are we doing here? We're putting trees into the river, so we're essentially doing something similar, right? So that makes a lot of sense to me, the 0.1.
Yeah, it's a good point, Chris.
Perfect.
Maybe it's a little thicker than your typical forest because you've got them all kind of woven together. Well, although some of them aren't. So anyway, yeah.
Definitely. Yeah, so you can see that how we've kind of implemented those two types of features, at least along just this transect here. One thing I wanted to bring up as we were discussing at the beginning of this podcast that the use of laterally varying Manning's end, I do that pretty much almost always, especially for transects here or the entire valley wide. So there's generally usually something changing. For this location, we're using 0.45 for the channel bed, so we're using Ben's number. For the immediate overbank areas, and particularly on this right bank side of the transect, we're using 0.06 because that's farmed land. It's closer to like tilled or maybe has some low growing vegetation on it. And then once we get up and out of the floodplain here, we go to 0.08, which is kind of like an open forested area and or maybe a home with some structures and, farming equipment.
So I do want to make sure, Robert, that we leave enough time to discuss some of the 2D benefits of restoration modeling. So what sort of results did you get from this analysis?
Definitely. So here I have a quick visualization of what those results might look like. So this table is values of the difference of running the hydraulic model without the restoration elements and then with the restoration elements and then taking the difference in the velocities. Here I picked out that transect we've been mentioning where you have your logjam feature, which is causing quite a bit of velocity reduction in the channel, which is the point of adding those elements to this section, as well as these embedded logs is decreasing the velocity. Part of that though, you can see that velocity is increasing between those elements as it squeezes past and rushes through that section. So that's something to pay attention to, especially for considering scour in this design.
Really quickly, just because I'm sure there's some people that are thinking about this. How did you get so many slices in a cross section of velocity? Because a lot of people just know how to get a leftover bank, a channel, and a right over bank velocity, but obviously you get a lot more detail here. How were you able to do that?
Definitely. So in the 1D calculations, it only calculates one velocity for the channel, for the transect. But there is an option, and I believe it's in the computational options or in the 1D plan, where you can ask HEC-RAS to slice your channel, your left over bank, your right over bank into a number of slices. So it still applies that one computed velocity for that channel, but it will use the hydraulic properties of those, for in this example, 20 slices to extrapolate what that velocity might be for that slice.
Cool. Thank you.
Yeah. So an added visualization to this, and I'm a very visual person, so 1D can actually be a struggle for that. I put those tabular results directly laid out onto the map here, where you can see darker red is reductions in velocity due to the elements, and green is increase in velocity. And once you start looking at how those 1D values are placed spatially on the map, you can see that it's working relatively well. You're capturing the elements in their space and how water is moving amongst them. And then from that, another part of the calculations that we're interested in for these conceptual designs is its overall effects to channel velocity and to the difference in water surface elevation due to the elements. And you can see here, these last 5 rows are rows that have stream restoration elements implemented. And you can see that the water surface elevation is rising due to the increased roughness, channel velocity is decreasing for the same reason. And then you can see that effect perpetuating to the other transects that are upstream, with kind of diminishing returns to see how that affects your stream reach in general, on a more of a reach wide perspective rather than just transect by transect.
For sure.
So the bottom line is, I think if you've got a lot of experience in doing these kind of features, walking streams, knowing rivers, knowing about geomorphology, you can look at your 1D results and look at the plan form of the river and the tendencies of the river to scour and deposit. And you can make some pretty good assessments about where to put these features, what kind of features to put in, and how frequent, and then what your expected benefit would be, or potential negatives too would be to those features. And then you use this 1D output to kind of verify your assumptions and maybe give you a little bit more of a quantitative feel to what's going to happen or what you might expect. But ultimately, I think too, a lot of this stuff, and tell me what you think, Robert, but I see this as a lot of, hey, let's get it in here. We're going to do our best to design it to stay in place and hit the criteria we're trying to hit. But the reality is, some of this stuff may eventually wash away into the
Mhm.
river and may be temporary.
Yeah.
Mhm.
One question, Robert, for you, because again, looking at this, it might be a question that folks have. So there are a couple features in here, particularly the boulders at the upstream end of this image that don't have a cross section associated with them, but you can still
Mhm.
see the velocity impact that those are having at your cross section there, where it's
Mhm.
slowing down velocity. How did you account for restoration elements that don't run through a cross section? And I was talking about so when I said I should have said downstream. At the downstream end is the boulders
Here.
right there. Yeah.
Yeah.
How do you account for that without having a cross section go through them?
Yeah, it's definitely a lot of what I learned from the project, because you're trying to utilize so many different parts of the project, keeping it similar to what it was so that you have some frame of reference to other computations and other model alternatives. But you're also trying to add resolution and add details to this model, so that you can see it working appropriately. In this specific example, each of these 1D results has been applied to the transect that's just downstream of it. Flow is moving from left to right in this image. So we are taking some liberties and using some intuition to try to make the best of the transects that we have and can enter into the model, and apply those features to them.
Yeah.
And then being aware that we need to maybe not take the exact spatial definition of these transects at face value, but we need to reinterpret, what that would look like for our site.
Sure. Yeah. That makes a ton of
Is
sense.
there any particular reason why you didn't want to interpolate a section to go through those boulders on the downstream end?
Yeah, a lot of it. So a lot of what we're trying to do, and I bet you could talk about a lot more about best practices, that we want the transects to be relatively equally spaced. That's just a good practice, I suppose. So in that effort, we equally space these transects, but that leaves those boulders pretty much smack dab in the middle of the two. So once we started applying these elements to these transects, it was apparent that we kind of wanted to represent that boulder field on the transect that's downstream of it.
Mhm.
But primarily we uh, set up the transects first, and then put the elements on it to try to prioritize the modeling best practices versus like absolutely capturing all these elements exactly where they're drawn.
Yeah. Awesome. Well, this is great, Robert. Thanks for sharing this. This is
Mhm.
really, I love this figure in particular. I think it's very visually easy to understand how really well the one-dimensional modeling is performing for capturing some of the hydraulic effects that these restoration features have. Um, I do want to go through a rapid fire here just between the three of
Mhm.
us to brainstorm some situations where, again, maybe this 1D approach is warranted, maybe limitations of a 1D approach when it comes to restoration, and when you might want to move into a 2D space for this type of design. So, from what I took from this conversation, one of the biggest drivers for uh, this particular project and maybe other projects that people are going to elect to use 1D modeling for would be, a lack of bathymetric data, right? If you're limited to bathymetric data at particular cross sections, um, that might limit the effectiveness and accuracy of a 2D model in that space. I think that's certainly a reason to stick with 1D. Another one that you mentioned that is right on with this project is the fact that you had an existing 1D model, right? So there's a lot of projects out there that are budget or time constrained, might not have the ability to go through and develop an entirely new model. But if you have a 1D model, Robert's shown us some great ways how you can still answer some of these questions around restoration design with that modeling tool without going to 2D. Chris, I'm going to throw it to you. What are some things off the top of your head that are limitations, potential limitations of a 1D model when it comes to restoration design?
Yeah, well, first of all, I think another reason why 1D could be used confidently here is you had you have a team that has experience doing this work and knows how to interpret 1D results and apply those to a very three-dimensional issue, which is restoration features in a stream. But some of the downsides with 1D, you can get into the computations and how RAS discretizes the terrain in 1D. It uses cross sections. Cross sections are they produce a single water surface elevation across the entire cross section, and it calculates a single average velocity for that cross section. Now, as Robert showed you, you can break that up into your subsections or even finer with these vertical slices, so you can get a feel for how the velocity would be distributed. But that is purely based on conveyance. There's no momentum associated with that distribution. It's purely just a conveyance weighted distribution of velocity. So the way RAS 1D calculates water surface and velocity is a little bit of a disadvantage there, because these restoration sites are close in. You've got flow patterns moving in and around them in a very near field. So a lot of two-dimensional effects there that are just not going to be picked up with 1D. But this is where the experience comes into play, in my opinion, where you can look at your 1D results, you can look at how you're setting up your 1D model, and you can use that to basically project that into a 2D space based on how you understand water to flow in a river like that, with and without these features, how you understand the science of geomorphology and how that's going to be affected by these features, I think plays into it. So, and then besides the computations, now you've just got the feel of the software and how you can look at things and results. If you're used to 1D, obviously you're going to be drawn to that more. There are a lot of people today, especially younger engineers and modelers, who've never done 1D. They only do 2D. And so they're not going to want to do 1D here. 1D is actually really hard if you haven't done it. 2D is a lot easier. If you've done neither, I think 2D has an easier level of entry. But 1D has the history too. So you have a lot of different output options. We kind of looked at that earlier with respect to bridges, in that you've got that detailed output table that's been around forever, but it gives you a lot of information about bridges. Well, same thing goes for restoration features. You may want to use that detailed output table. You may want to use the profile output table, or all the profile plots are already created and well developed in 1D RAS, but are still kind of trying to catch up in 2D. So I think those are some of the things that come to mind for me anyways about 1D versus 2D. Personally, I think, we're moving towards more and more 2D, and I think that's going to be more and more common for restoration work. And it's obviously one of the big downsides of 2D is the time it takes to run these models. And when you get into restoration work, especially on the project you're working on, Robert, where you've got a long stretch of river, if you try to do all that in 2D, your model may take hours or even days to run, especially if you want to have any sort of resolution around these features, meaning small cell sizes, right? So
Yeah,
I think those are all.
We're modeling 20 miles, and we have 10 sites within those 20 miles. And we're really interested in how they interact as well, mile by mile. It takes 10 seconds to run 20 miles.
It's incredible.
And, yeah. And it helps us choose elements, right? The person I'm working with, puts his thumb out, and he has decades of experience to say, this is what it should look like. But I might be trying 100 things and using the results to inform what might be best. So the computational efficiency is huge.
Yeah, I mean, one of the rules of thumb that Chris and I was talking about in our 2D class is to start simple, add detail where needed. That's really catered towards a 2D kind of mindset, is how I viewed it. But I think it applies in this case as well, right? I think there's going to be a lot of models, especially in, a situation where you have an awesome calibrated existing 1D model, right? What's the simplest thing you can do with that? Keep it the same, right? And so doing that, and then potentially adding additional detail or potentially adding some 2D areas later on, that's the approach that should be done. I think far too often, like especially with younger inexperienced modelers that only know 2D, they're going to jump straight to that tool and I think they're causing themselves to potentially walk into some inefficiencies that are unnecessary. Particularly if you can be working with somebody that has so much experience, processing 1D results. A couple other things off the top of my head in relation to this discussion. One, we didn't talk about super elevation at all yet, which I think is an important idea. And it really not just super elevation, but any sort of water surface elevation constraints. Obviously, you can only get one water surface elevation per computed cross section in 1D RAS, which is a real limiter in certain situations. Now, I think this project, Robert, you were describing, there weren't any real sensitivities around water surface elevation in terms of like having to, stay under a certain water surface or having to have at least a certain water surface elevation. Yours was much more of a generalized, where am I slowing up water? How is that going to result in change to my geomorphology? A little bit more qualitative of a 1D analysis. I think in certain situations, if you're doing restoration design and you're having to make sure that that restoration design doesn't impact the low chord of a bridge upstream of it or something like that, where there's going to be some definitive quantitative results that you need to analyze, it's going to be a little bit tricky to get that with 1D just because we know there's going to be some variation in water surface elevation around these elements and how that kind of extends upstream. In the same way, if we have water surface elevations that are sensitive around a bend in the river and we have restoration elements there, you're not able to capture that super elevation that's going to occur as water moves around those features. You will be able to do that in a 2D model if you're using the full shallow water equation. So those are a couple things that stand out as things to consider. What is the restoration? Because not all restoration models are the same, right? We talk about river restoration as this general topic, but there are river restoration models like what you're working on, Robert, that are more generalized, a little bit more qualitative. We'll call them maybe more art than science, right? And then there are river restoration models that are going to be used for permitting, where you have to say this is going to maintain a water surface of X. And depending on what those objectives are, you're going to have different tools that you're going to want to use, maybe a combination of the two, but you're going to want to make sure you're using the right one. The last thing I'll mention, which is another important one and right up my alley, is sometimes these restoration features are designed for regulatory rivers where FEMA has regulatory authority over them, and you're going to have to show a no rise or submit a conditional letter or map revision to show that you're not impacting properties adjacent to your project site. That's going to be a lot simpler to do in 1D, especially with encroachment analysis. So if you are doing river restoration design, happens to be in a regulatory area, that could also be a reason to maybe stick with 1D for that particular project. So a lot of different things to consider, certainly pros and cons all around. I think my biggest takeaway from this conversation and the conversations that we had leading up to the podcast is just the importance of your comfortability with the tool as an engineer, right? If you are really comfortable and really confident in the results of a 1D model and you have experience interpreting those results, that's a good tool to use. Same with 2D, right? If you're really confident and really competent with 2D modeling, that's going to be a good tool to use. Where we start getting into a little bit of trouble is when we start extending ourselves into tools or methods that we're not comfortable with. And that's when you can make some mistakes, miss some things. So I think that level of comfort is something that's really, really important to consider when making these decisions. Chris, anything to add in closing out on the conversation of 1D and 2D restoration modeling?
I think you really hit on an important thing that we talk a lot about in our class, which is RAS is a tool. You have to know how to use the tool. You have to know how to interpret the results from the tool to make it a useful tool. And I kind of liken it to, I was just thinking about this, like, if you're framing up a house, you could do it with a hammer and nails. You could also do it with a 18-volt battery powered drill with a hex drill bit on it, and you could get the same thing accomplished, right? But somebody who's been framing houses with a hammer, they're going to be really skilled at that. They're going to be able to do it really quick. Even though the drill is maybe a fancier tool, it's more modern, maybe even holds together better than nails long term. I don't know. But the thing is, if you know how to use it, you're going to do an equally good job, I think, in a lot of cases. And I think certainly this 1D, 2D discussion for restoration kind of fits into that area. So
awesome.
Yeah, really good, Robert. I appreciate you sharing that with us. That was really cool. I like the way you did velocity distributions.
Mm-hmm.
I think I'm going to steal that.
Yeah, I think that's also a key takeaway for folks. If you're going to be doing 1D restoration modeling, to make sure that you have those velocity distributions broken up in your cross sections to maximize the utility of that as much as you can. Because,
but and going back to the know the tool discussion is know what that is.
Yep.
That is not a true two-dimensional representation. That is just a velocity distribution based on conveyance.
Yep.
And so that's different. It gives you a pretty good idea, but it's not the same as a 2D model based on the full Saint Venant equations.
Yeah. Well, it sounds like we have another topic, maybe, Chris, that we can talk about. Do a little comparison of 2D and 1D velocity distributions. That might be a topic.
All right.
Sounds great. Awesome. Well, thanks again, Robert. This has been really awesome. I do want to preview our next episode. So coming up next month, we will be talking about nature-like fishways, 2D nature-like fishways, how to model those, what end values to use for those types of designs. Nature-like fishways are one of those projects that are becoming more and more common as we're kind of adding robust fish passage facilities to hydro projects around the U.S. We're going to have some guest speakers for that podcast. So kind of similar to this, we're going to bring in people that know a lot more than Chris and I on a particular topic. And hopefully they do as good a job as you did, Robert. This is great having you on today.
Yeah, thank you.
Awesome. Thanks, Robert.
Well, Chris, any closing words?
Come check out our classes, and if you happen to be at USSD or ASFPM, come find me or Ben respectively. We'll be there hanging out and having a good time.
Awesome. Well, thank you again, everybody, for listening today. Hopefully you found this informative. This has been Full Momentum, an HEC-RAS podcast. Until next time.